Myself Punyamurthy from Department of Chemistry, IIT Guwahati. I welcome you all to IIT PAL program. In this class, we will study about hydrocarbons. Hydrocarbons are the compounds that contain only carbon and hydrogen atoms. Examples: methane, ethane, propane, and so on. You can go on butane. You can have, if you look at this compound, it has only one carbon, is bonded with 4 hydrogen atoms. Here you have 2 carbon atom, and they are bonded together, and also in addition to that, each carbon is bonded with 3 hydrogen atoms. This is called ethane, and if you have 3 carbon atoms, is called propane, and 4 is called butane. You can go on like this. So, they play, they are important source of energy. You must be familiar with LPG, CNG, petrol, diesel, polythene bag, paint, drug, and so on. If you look at LPG is abbreviated form of liquefied petroleum gas. We use as fuel in home, and CNG is compressed natural gas, and petrol, diesel, they are obtained by fractional distillation from petroleum, that is obtained from earth's crust. We use them as automobile fuels. Polythene bag, and this is a material, this also ethylene is involved, is hydrocarbon to make this material, and we use as a polythene bag. And similarly, hydrocarbons also find applications in drugs as well as in paints and so on. Therefore, they play a key role in daily life. So, hydrocarbons can be classified broadly into 3 types. So, just we have seen fuels is a mixture of hydrocarbons, and now let us, they can be broadly divided into 3 types: saturated hydrocarbons, unsaturated hydrocarbons, aromatic hydrocarbons. Examples: saturated, just we have seen ethane, propane. If you look at these molecules, they have a carbon-carbon single bond. The hydrocarbons that contain carbon-carbon single bonds, it can be linear, it can also be cyclic. This molecule has 3 carbon atoms, the linear molecule. Here also has 3 carbon atom, right? You have this has 4 carbon atoms, it is closed one. This is called cyclopropane. This is propane. And these are examples for saturated hydrocarbons, compounds that contain carbon-carbon single bonds. Unsaturated hydrocarbons, compounds that contain carbon-carbon multiple bonds. For examples, this molecule has a carbon-carbon double bond, and so you can write like this: its carbon is bonded with 2 hydrogen atom, again bonded with carbon, it has a carbon-carbon double bond. So this molecule has carbon-carbon triple bond. So these compounds are called unsaturated hydrocarbons. This also can be cyclic. For example, when you have the 4 carbon atoms, it can be cyclic. So whenever you have the carbon-carbon multiple bonds, double bond, triple bonds, those hydrocarbons are called unsaturated hydrocarbons. The difference between these 2 hydrocarbons is it has 2 hydrogens less. This is C2H6. So they have general formula for the linear one, CnH2n plus 2. This is a common formula for the saturated hydrocarbons, linear hydrocarbons. Cn 2 carbon and hydrogen is going to be 6. And if you compare these two, this compound has 2 hydrogens less. Comparing to that, they have the common formula CnH2n. And this compound has 4 hydrogens less comparing to the alkane, 2 hydrogens less comparing to the ethylene. This more unsaturated hydrocarbon, this example. This is called ethylene and this is called ethane. They have the common formula CnH2n minus 2. So this is the name of this compound is ethane. You see the difference, ethane. So in this case, the ANE is converted into ethene, right? A is changed to ethene. And in this case, the A is converted, E is changed to Y, ethine. These are the names of these compounds. You can go on like this. If you increase one more carbon, is called this is propene. Propane, this is propane. This compound is propane, A is changed to ene, propene. If you have the corresponding this one, triple bond, then propyne. Can go on. Anyway, these are the examples for unsaturated hydrocarbons. And if you look at all the compounds, they have only carbon and hydrogen atoms. Aromatic hydrocarbons. So these class of compounds have a benzene ring as unit. Say for example, if it can be benzene or derivatives. So here what happens, you look at this compound is a cyclic compound, you have the double bond, single bond, double bond, single bond, double bond. That means it has 6 carbon atom and is bonded with the carbon is bonded with another carbon, double bond, and at the same time you have the CH one single hydrogen atom. So this compound is called aromatic compound and also this is derivatives, right. So one of the hydrogen is replaced by methyl group called methyl benzene and this is benzene, and this you have one more ring is this called naphthalene. So, these also hydrocarbons, look at it, they have only carbon hydrogen atoms. So, these kind of compounds is called aromatic hydrocarbons. In this class, now let us focus on alkanes. Just we have seen saturated hydrocarbons, those are called alkanes. And the first member of this series is methane. If we replace one of the hydrogen with methyl group, then we get the next series ethane. This is called methane, this is ethane. You can go on, you replace the hydrogen, you will get propane, butane, or the corresponding alkanes. First, let us look at the structure and bonding of alkanes. So, this is the structure of methane. You can look at this structure is the methane. Look at it, carbon is bonded with the structure of methane. It has tetrahedral geometry. If you look at it, it has a tetrahedral geometry. And so, the bond angle between this is 1095 degree. The bond length is 1.09 Armstrong, this bond length. And this carbon involves sp3 hybrid orbital, sp3 hybrid orbital that overlaps with s orbital of hydrogen, you make bond, the sigma bond. The sigma bond, the carbon has 4 CH sigma bonds. These bonds are made by overlapping of sp3 hybrid orbital of the carbon with the s orbital of hydrogen, you make 4 sigma bonds. Now, let us go for ethane. So, this sp3 orbital of this carbon overlaps with sp3 orbital of this carbon, you make a carbon carbon sigma bond. In addition to that, this one of the sp3 hybrid orbital of this carbon overlaps with the hydrogen s orbital, make another sigma bond. Similarly, overlapping of this sp3 orbital, carbon sp3 hybrid orbital with this hydrogen make another sigma bond. So, this is the structure of ethane. If you look at it and you have the carbon carbon sigma bond, this is formed due to the overlapping of the sp3 hybrid orbital this carbon with the sp3 hybrid orbital of this carbon to form the carbon carbon sigma bond. In addition to that, there is a carbon hydrogen sigma bond. There are 3 hydrogen carbon carbon hydrogen sigma bonds in this carbon, and which is formed due to the overlapping of sp3 hybrid of this carbon with this hydrogen s orbital, similarly this one. The bond length between these 2 carbon, this bond length is 1.54 Armstrong, this is 1.09 Armstrong, this one. So, the carbon hydrogen bond length is 1.09 Armstrong and this carbon carbon bond length is 1.54. This is the structure and bonding of methane and ethane. You can go on like this for other alkanes. Just we have seen the structure of methane is ethane, they have tetrahedral geometry, and so they involve they have carbon 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 hydrogen sigma bonds. Now, let us see the nomenclature and isomerism. So, methane, ethane, propane, they have only one structure. Methane and ethane, propane, they no problem. We can call methane, ethane, propane. When you go for butane or higher alkanes, butane. So, there are 2 structures possible for this molecule. So, one is the linear one. The other alternative, we can also have other structure. So, both have same molecular formula C4H10, C4. So, they have same molecular formula, but different structures, they show different properties, the boiling point is different. So, to when you go for pentane further, there are 3 structures possible. We look at these molecules, they have C5H12, C5H12. C5H12. These 3 compounds have same molecular formula C5H12. However, they have different properties, different structures. to name these compounds, IUPAC, International Union Pure and Applied Chemistry, have introduced some rules to distinguish these compounds, to name these compounds, that is called IUPAC nomenclature. So, using this IUPAC nomenclature, you can name all the compounds. But when you go for hexane, you will have more structures, and heptane you will have with 7 carbon atoms, and octane 8 carbon atoms, nonane 9 carbon atoms, decane 10 carbon atoms, you will have number of structures. Using this nomenclature, and you can name all the compounds. This is called IUPAC nomenclature. And let us how you will name these compounds. To name this compound, you have to follow some guidelines. And so, first what we have to do, we have to find out the linear alkane, there is no problem. You can there are 5 carbon atoms, you can call pentane. When you go for branched one, and so what we have to do in this case, we have to find out the longest chain in this molecule. And you can, there are 2 possibilities, 1, 2, 3, this is one chain, you have 3 carbon atoms. The other possibility is there 3, 4. So, you can name like this, then one chain you have 3 carbon atoms. If you name like this, it comes 4 carbon atoms. So, you have to find out the longest chain, you have to start numbering the chain, you have to, other words, you have to find out the longest chain in the molecule. So, in this molecule, this is the longest chain, right, not this one, you have only 3 carbon atoms. If you go in this way, you have the 4 carbon atoms. You have to find out the longest chain in the molecule. Once you find the longest chain, now you have to look at it, you have to start numbering the compound. So, already I have done before the numbering, but first you have to find out the longest chain, then you start numbering the longest chain. How will you there are 2 ways you can start numbering, from here or there. You can start numbering from here, this is the right one. If you start numbering here, there is the wrong one, but what you have to do, you have to start numbering where the substitution is present, closer to the end. So, if here, if you look at it, this one, the substitution is present closer to this carbon, this is the end, and you have substitution is present here, therefore, you have to start numbering from this carbon, not from this side. So, once then numbering is done, now you have to combine, you have to find out the substitution position and combine this one and with that one. And in this case, you have the methyl group. So, just we have seen when you have 4 hydrogen atoms, we call it as methane. So, when you replace one of the hydrogen, you write, then we call it methyl. So, this is methane. When you remove one of the hydrogen, you have the CH3, then we call it as methyl. See, the AN has been replaced. Similarly, this is ethane. The AN can be replaced, for example, and so this is ethane, right. So, when you have this one substituent, what happens in this case? One of the hydrogen has been replaced. So, this is called ethyl, right, ethane, ethyl, that AN has been replaced by YL. Similarly, when you go for propane, then when you have the CH3, CH2, CH2 substituent is called propyl, butyl, pentyl, so on. So, now what we have to, you have to bring the substitution as prefix, and this in this case, and position is 2 methyl butane. It has 4 carbon atoms. So, the substitution is present on second carbon atom, the present substitution is methyl group, therefore, 2 methyl butane. The name of the compound is 2 methyl butane. So, now let us look at this molecule, and this is a, you have to find out the longest chain. Anyway, in this both ways same, there is no problem. Then you have to start numbering the chain has 3 carbon atoms, the substitution is present and second carbon atoms. So, you have to write 2, 2 dimethyl propane. So, if you have 1 carbon atom, we call methane, 2 carbon atoms of ethane, 3 propane, 4 butane and pentane, 5 carbon atoms, 6 hexane, 7 heptane, so on. And in this case, you have the chain has 3 carbon atoms, and the second carbon atom you have the 2 methyl group, and so 2, 2 dimethyl propane. The name of the compound is 2, 2 dimethyl propane. Here 2 methyl butane, this is pentane. So, in this way, once if you understand this one, you can name all the compounds. So, now let us look at this one, and in the case of butane, and one is a linear structure, another one is branch structure. This called butane, there is no problem. And name of this compound is the, now you have to start numbering this compound. Here also no problem, you have either way you can start numbering, you have 3 carbon atoms. And now you have to find out the presence of substitution, position of the substitution at present and second carbon atom. So, you have to write 2 methyl propane, 2 methyl propane. Now, let us name this compound. So, this how will you name this compound? First, now we have to find out the longest chain in this molecule. The longest chain is this one, right. So, longest chain has 6 carbon atoms. This is the longest chain. Once you find, after finding the longest chain, then you have to find out where the substitution is. Now, this is a 2 terminal is present in this side and that side. You have to find out which carbon, which end is very close to the carbon that contains the substitution, in this case here. So, you have to start numbering from here. So, numbering is done. Once numbering is done, you have to find out the position of the substitution here, the present and second carbon atoms, and in this case present 4 carbon atoms. So, now you have to write 1, 4 dimethyl, that means 2, 4 dimethyl, the methyl group present at second carbon atoms and 4 carbon atom, dimethyl hexane. This IUPAC name of this compound. So, next the primary, secondary, tertiary carbon atoms. Let us look at this molecule. Or methane. Methane, or that carbon contains bonded with only one carbon, is called primary carbon atom. So, this carbon is bonded with, otherwise you can call terminal carbon. It is bonded with one carbon atom, is called primary carbon atom. And in this case, the carbon is bonded with two carbon atoms, right, one with the tertiary, another one is the primary. This is called secondary carbon atom. When the carbon is bonded with these 3 carbon atoms, 4 carbon atom, this is called quaternary carbon atom. This is called quaternary, is bonded with 4 carbon atoms. On the other hand, if it has this is called tertiary carbon atom. So, this means this carbon is bonded with 3 carbon atoms, right, and if it bonded with another carbon, we call this quaternary carbon atom. This is followed the nomenclature. Now, let us look at the isomerism. So, butane, it can have 2 structures. So, butane and 2-methylpropane, and they have the same molecular formula C4H10, but different structures, right. So, they have different properties now. This boiling point is different, these 2 compounds. So, the molecules have same molecular formula, but different structures, different property. They are called structural isomers. So, the relationship between these 2 compounds are structural isomers. Molecules have same molecular formula, but different structure, they are called isomers. The relationship between these 2 is structural isomers, right. For pentane, we can have three structures. They have different physical properties, and these are called structural isomers. They have same molecular formula C5H12, right, all have C5H12, but they have different structures. The relationship between them is structural isomers. So far we have seen classification of hydrocarbons, structure and bonding of methane and ethane. They have tetrahedral geometry, but the bond angle 109.5 degree, and they are non-planar molecule. Then we have seen the IUPAC nomenclature and isomerism of alkanes. Now, let us see the preparation of alkanes. Petroleum, natural gas are the main source of hydrocarbons. Natural gas contains 80% methane, 10% ethane, 10% higher alkanes, propane, butane, so on. This is a mixture of natural gas, and petroleum contains hydrocarbons up to C40. It is a mixture of hydrocarbons. They are found in the Earth's crust together, and so we will see them in detail later. Now, we will see the other methods that we use in the laboratory to prepare alkanes. So, one of the common reactions we use in the laboratory to prepare alkanes from alkenes and alkynes. Hydrogenation of unsaturated hydrocarbons. The beginning we have seen ethylene and acetylene as unsaturated hydrocarbons, and when you react, for example, propene or propane, these unsaturated hydrocarbons with hydrogen. Here you need 2 molecules of hydrogen, and when you treat this alkene with hydrogen in the presence of catalysts like palladium charcoal or platinum or nickel, the alkene can react with hydrogen. Basically, it undergoes addition, you get alkane. Similarly, alkane can be transformed to it's a stereospecific reaction, and what happens in these reactions, you have your catalyst, for example, palladium charcoal, the palladium charcoal, when you treat exposed with hydrogen, hydrogen absorbed from the surface, you form activate the hydrogen, you form this kind of intermediate. Once if you have this intermediate, the hydrogen is absorbed on the surface of the catalyst, your alkene, when you treat this with your alkene, the alkene also can bind with your palladium by interaction, bicomplex formation. You have for example, you have this kind of intermediate. Once if you form this intermediate, the hydrogen can transfer intramolecularly. So, now you have the hydrogen is transferred, you have already carbon, you will have this kind of intermediate. So, you have another hydrogen here, this can transfer, again you have the reaction medium has a lot of hydrogen, the hydrogen can absorb here, it can transfer to another carbon. So, you will generate the reduced alkane and your catalyst is regenerated. So, now again it can react with the hydrogen gas, it can go on like this. So, whenever you use less than 10 mole % of this, metal with respect to a substrate, we call it as catalyst, and it can go on like this with another hydrogen, it catalyzes like this reaction. So, this commonly used, anyway, this very simple alkene, but when you have a larger alkene, for example, actine, nonene, then very easy to reduce in the laboratory, and we can get very pure reduced alkane. So, in the case of alkyne, what happens? A similar way, first what happens, the alkyne is reduced to alkene, it depends upon the catalyst, what you use. The catalyst active, the alkene can be further reduced to alkane. So, it involves, it requires 2 molecules of hydrogen and it requires 1 molecule of hydrogen. And in this reaction, what happens? Alkene, when we study the alkene and alkyne, you see the structure, the alkene is a planar molecule, alkane is a non-planar molecule, right, tetrahedral geometry. The alkene is a planar molecule, you have the top face or bottom face, and your hydrogen is on the plane, right, and the alkene approaches the catalyst like this. The bottom side, the one hydrogen transfer, then right, the another catalyst and hydrogen is there, another hydrogen comes. Basically, both hydrogen are transferred the same phase of the alkene, you get the alkane. The reaction is, the addition is syn addition, the reaction is stereospecific, and same thing happens in the case of alkane also. Right, the alkane approaches like this, the both hydrogens are transferred the same phase of the alkyne, then you get the alkene, that alkene again further react and you get the this reaction also syn addition reaction stereospecific. This is one of the common reaction we perform in the laboratory to make alkanes from alkenes, alkynes, very easy reaction. The second example is reduction using Niacin hydrogen. If you have alkyl halide like bromomethane or bromooctane or any except it can be chlorine or it can be iodide, no problem, but if you have fluorine does not react. When you react, when you treat bromomethane with zinc HCl, so it can be reduced into methane and HBr. So, this is a reduction reaction. If you have alkyl halide like bromo, chloro, iodo halides, you can reduce them to the corresponding alkane, you generate the hydrogen halide as a byproduct. This is another reaction used to prepare alkane. The third example is Woods coupling. Alkyl halide, for example, bromomethane can be cross coupled together. If you have take 2 molecules of this, react with 2 equivalent of sodium, you can generate ethane, symmetrical alkane with 2 molecules of sodium bromide. This is called Woods coupling, and this reaction what happens? This bromomethane reacts with sodium, you generate once you form this intermediate, this can react with another molecule of bromomethane, you get ethane and sodium bromide. So, you generate 2 molecules of sodium bromide and ethane. This is good to make symmetrical alkanes. But if you take a mixture of alkyl halide, for example, methyl bromide and ethyl bromide, will not be good. You will end up with mixture of compounds, 3 compounds. For example, instead of methyl bromide, you take a mixture of methyl and ethyl bromide. When you react these 2 bromides with 2 equivalent of sodium, you will end up with mixture of compounds. You will have ethane. This can be formed from the reaction of this methyl bromide. In addition to that, you will also have these 2 molecules can react, then you generate butane, and if they couple together, you will get propane. Basically, you will end up with mixture of 3 compounds, ethane, propane, butane. It will be very difficult to separate these hydrocarbons. Therefore, the Woods coupling is very good to make symmetrical alkanes. So far, we have seen 2 methods, only hydrogenation of unsaturated hydrocarbons like ethylene and alkyne to alkanes. Then we have seen the coupling of the reduction of alkyl halide to alkane using zinc HCl, and where you generate Niacin hydrogen that reduces alkyl halide to alkane. Then we have seen Woods coupling, and it will be good to make symmetrical alkanes. The next reaction is decarboxylation. Reactions. If you have, for example, sodium acetate, sodium carboxylate, when you treat sodium carboxylate with soda lime, when you heat, and so you generate alkane. So, the byproduct is sodium carbonate in this, and this is one of the method used to make alkane. This, whenever you treat sodium carboxylate with soda lime and heat it, you can generate alkane, and the byproduct is sodium carbonate. This is called decarboxylation reaction. You lose 1 carbon in this. Instead of 2 carbons, you will get only 1 carbon less hydrocarbon alkanes. The last example is Golf synthesis. You can also, if you have the sodium potassium carboxylate, for example, sodium acetate, when you do electrolysis, it can be converted into symmetrical alkane ethane, and you will generate sodium hydroxide. When you do electrolysis in water, so you generate sodium hydroxide and carbon dioxide, hydrogen and sodium hydroxide. This will be the byproduct. This is also very common method to make alkanes. How the reaction takes place? Anode, it can lose 2 molecule of, if we take sodium acetate, it can lose 2 electrons and you generate the radical. This radical can release carbon dioxide, you generate the methyl radical, 2 methyl radical. These 2 methyl radical combined together, you generate the ethane. This is what happens at anode. At cathode, water, you have 2 electrons, then you generate OH minus plus H dot. So, it can be now this OH minus can 2 OH minus already have the case the anode you have 2 sodium plus, they can react together. Yes, you take 2 molecule of this, take 2 and then you generate and this 2 can combine together, you generate H 2. So, at cathode it takes this 2 electron, reduce the water is converted into hydrogen gas and sodium hydroxide. At anode you generate the alkane carbon dioxide. So, with this I conclude today's lecture and we will see alkenes, alkynes the next lectures. Thank you very much.